So we have an assignment that's due, what, in a week or so? About a week? A week today? Yeah. Do get a crack at it on the weekend and try to get that behind you. So last day we didn't finish all this material that I want to talk about on QQ plots. So we'll spend a fair bit of today about it and hopefully into the next topic as well. So just to remind you from last day, we've got these quantile-quantile plots, and what we've been looking at is the actual quantiles from a couple of particular distributions. So there's no data involved here as yet, right? We're just looking at what do the shape of the quantile functions look like when you compare them one to another. And the advantage of the quantile functions, we can actually match them on the proportion p that we're looking at. So for every proportion p, we can get the quantile function for the distribution of x and also the quantile for the distribution of y, and plot that curve. So that's a parametric curve, parameterized by p, and look at that shape, okay? And when we do that, when they're exactly the same distribution, of course, you're going to get things fitting on, that curve is going to just be a straight line because q of x equals q of y for all p. If the two distributions are related simply by a location scale change, that is, the distribution is the same in every other way, the same family distribution, just different location and scale, you'll also see a straight line appearing. It's just that will have a slope and intercept corresponding to the scale and the location change. So we looked at all this last day. And now if you look at a particular distribution, as we commonly do, look at a normal distribution, it doesn't matter what mean or variance we choose, because that's just going to affect the slope and intercept of the line if it's the same distribution. We look at the quantiles of a t on 1 degree of freedom of Cauchy distribution compared to a normal or Gaussian, and see that the tail in the t distribution is stretched out on either end, stretched out farther away from the middle. So you want to get some practice at interpreting these curves, at what they say about the relationship between one distribution and the other. So again, t on 3, same phenomenon, that the tail is pulled out on the high side and on the low side, sort of matches it in the middle, and not pulled out quite as far because it's got more degrees of freedom, so it doesn't have quite as heavy tails. 10 degrees of freedom, it's still there as well. The curvature, the tails are pulled out a little bit on either end, but not quite so much. What's sometimes helpful is to add a straight line to the plot, and think about a straight line that goes through the middle, mainly here, and gives you some sense of how can you tell that that tail is farther away. So if I'm imagining that it's a Gaussian distribution on the horizontal axis, I would expect, and it was supposed to be a matching distribution on the vertical axis, I'd expect that curve to be closer to this red line. The fact that it's farther away from the middle, means that that tail is pulled out. Same thing on this side, this tail is farther away from the middle, so it's being pulled out in that direction. So this has got a heavier left tail and a heavier right tail, that is more probability mass moving farther away than you'd expect to see in a Gaussian. Any question? Tails, same thing you can do with a skewed distribution, like a chi-squared distribution. If you add that line on there, you'll see that on the top, this is a chi-squared, I think on 1 degree of freedom, that it's farther away from the middle than you would expect from a Gaussian. So it's got a longer right tail. Conversely, on this side, imagine this red line continuing down here. I might expect it to be out here if it was Gaussian, but it's much closer to the middle. That's a shorter left tail. So it's pulled in on the left and pushed out on the right. Okay? And less so as the degrees of freedom increase, which you should know about limiting behaviors of chi-square distributions becoming more and more Gaussian looking as the degrees of freedom increase. Similarly with a mixture distribution, you can see agreement on one end, then there's a thin area in the middle, and then agreement again. This is a mixture of two different Gaussian distributions, depending on the location of those modes and also the fraction that's being mixed. So you see that kind of behavior, you know you've got a bimodal distribution compared to a Gaussian unimodal distribution. Okay, so that's all just theoretical against theoretical. No data at all. But those are the canonical shapes that you want to be looking at. Any questions? Sort of where we ended last lecture. When we have some data, I'm going to have my hypothesized distribution here, this on the x-axis, on the horizontal axis, and then the actual data, the estimated distribution on the y-axis. And the estimated distribution is just going to be the ordered values. The p I'm going to match them on is going to be something that doesn't ever get to be 1, because that matches things off at infinity. So I'm going to subtract off a small amount here, a half, from the index and divide by n. Okay? So it never gets to be 0, never gets to be 1 on either. So you don't get the minus infinity and plus infinity to try and match on. Okay? So for the Geiser data, the duration of the old faithful Geiser, we see that particular shape. And what we saw before when we were looking at the theoretical quantiles, on the vertical axis are the estimated quantiles from the data, the sample quantiles. On the horizontal are the normal quantiles. And so we see this kind of behavior like we saw before. Looks like a mixture distribution. Okay, I've got a mode here, a thin part, and another mode up here. So a mixture of two normals might be an interesting way to model the duration. Okay, it's definitely not a Gaussian distribution. Any questions? Okay, that's where we ended last day. Okay. So let's look at another data set, South African heart disease, again looking at the systolic blood pressure. And we have two groups, those with family history and those without. So I'm going to look, first of all, in R there's a QQ norm function which is going to compare the sample quantiles to Gaussian standard quantiles. And then I'm going to look at each of the plots by family history or not. Okay? So there's all of the data for the systolic blood pressure all together, marginalized over the family history. So we've got both kinds of family history in there. Comments? So first thing, does this look like it could be normally distributed? All those in favor, it could be normally distributed, hands high and proud. All those people that think it might not be normally distributed, hands high and proud. We're looking at a rough split, maybe half the class. Okay, those that think it shouldn't be normal, any suggestion what it might be? What makes it not look normally distributed? The skewness. Okay, you voted for it to be normal. Now you're saying it's approximately normal, but it's skewed. You can't sit on the fence. Yeah? Okay, so he thinks he remembers the chi-squared having a bit of curvature like this. If you imagine a straight line going along here, connecting as many of these dots as you can imagine, or a rough fit to that, you see that these points are farther away from where that line would be. So it's a longer tail on the right, and they're closer to the middle on the left. So it looks sort of like a short left tail, long right tail. It does look skewed. Okay? Everybody see that? Yeah? Okay, here they are individually. So no family history on the left, family history on the right. You see that curvature present in both of them. Perhaps more curvature here when there's no family history than when there is, but still some curvature. Yes? Where do you see that? No family history or family history? Has family history? Here? Here? So you're where do you think it's stretching out, and where do you see a second mode? Where? Here? This group here? Or this little bit? This little bit here? Okay, certainly it's piled up. There's a little bit of a bump there. What about here? Or here? Yeah, well, I see a flat spot here. I see a flat spot there. I see some flats. I mean, why are you? Yeah, but I wanted to see that I want to see the modes, and I want to see a thinning between them, right? So, I mean, want to be careful about over-interpreting these things. So the very coarse kind of description that's curvature up here, you know, have this, you might want to think there's a space there. I don't know why. Maybe it looks like there's certainly some granularity in the data here in the measurements. You can see lots of little flat spots. That's probably related to how fine the measurements are taken, the systolic blood pressure, that there's some ties in the data. We have to, it's a little tricky about interpreting this. At least you can see certainly there's some curvature there. That doesn't look like a straight line, right? And knowing the curvature, you can say how it's pulled out on longer right tail, shorter left tail. Okay? Typical exam question. So this is what we came up with. There's some ambiguity in these QQ plots. It seems to be a bit of an art form that you're trying to decide whether or not it's really something we should worry about. Is it that different? Could I imagine a normal sample producing it or not? And so we might think, well, how variable are these things? So I'm going to look at a bunch of samples of size 10 from normal 0-1 distribution. So these are, honest to God, Gaussians. So there are 4 QQ plots, normal QQ plots, with a y equals x line added, I believe. Yep, y equals x line added. So you might think, well, do they look like they could be from a normal distribution? Do these? Does it look like there's curvature there? It look like there's curvature in this one. You might think that, you know, there's some problems here that I don't believe that that's normal, but we know there are. They're all Gaussian. We generated them from Gaussian. So that's what standard normal looks like when you actually look at the sample. So you're going to see variability from sample to sample. So you have to be a little cautious about over-interpreting these things, particularly for small sample sizes. It's sample size 30. Same sort of things. Now things look a little more like a straight line. So that, you know, looks like you might say that was Gaussian. This one, well, I don't know. There's a bit of curvature in the middle there that pops up. This one down here, it's got some strange behavior on the tail. Both of them have that. But they're definitely looking more like a straight line. As the sample size increases, you do a better job at being able to tell, at least the middle part of the data, whether it looks Gaussian. So 50. Increase in sample size. Those are all normally distributed data. So those are pictures that you shouldn't get that excited about. It does look kind of Gaussian. All right? So there's still considerable variation from sample to sample in these things. And we're trying to make this less of an art form and a little more of a science, trying to figure out, should we be concerned about these data look like they don't come from the hypothesized distribution or not. So what I'm going to use is a package called QQ Test, which is going to try to incorporate visual testing in the QQ plot itself. And so what we're going to do, what QQ Test does, is it generates many, many, many samples, default 1,000. It'll generate 1,000 different samples from your supposed distribution of the same sample size as your data set. And then for each sample, we will have a corresponding sample quantile, right? So for each sample, I'll have the ordered data, which means I've got now 1,000 replications of the smallest value from a sample of size n. 1,000 repetitions from the second smallest value from a sample of size n. So I can use these to try and get how unusual are these things. Okay? So here, more precisely, what I want you to imagine that I'm doing here is, let's just put on the front lights here for a second, is I'm generating one sample. So this is sample 1. I get little n values, little n values of x, and I sort them. So here's the smallest value, the second smallest value, to the nth smallest value. And now I do that again, get another smallest value, second smallest value, etc., x, n smallest value. And I do that, let's say, 1,000 times. x2 to xn. Now these are all different values, so I'm going to just give them a superscript here, right? That's the first, from the first sample, from the second sample, all the way down to the 1,000th sample. So imagine I've got just this big Excel spreadsheet, right? So in this first column, I've got the smallest values from 1,000 different samples, smallest values from, second smallest from 1,000 different samples, etc. Well, now in this first column, this looks like a sample of size 1,000 of the smallest values from samples of size n. So this, any one of these columns, just give me some idea of the distribution of the smallest value or the second smallest value, etc. So I can use these, you know, go in 2.5% on either end, or 5% on either end of these. So order these guys, go in 5% on either end. Those 2 points will be identify the 90% central group, okay? An estimate of the percentile. So I can use each one of these to identify what is the usual case when I sample from that distribution. And I can do this because, remember, I've got a hypothesized distribution, so I can generate things from it. Nothing to do with the data, right? But this is what data from that distribution looks like. So you can read this at your leisure. It's a little more carefully worded. But the idea is then, if I look at a QQ test, now I get a QQ plot. So there's my data from duration just as I had before, but I have these gray envelopes, these gray bands. And what are they? Well, for the smallest value, it ranged from here to here. 99% of them were from here to here. 95% of them were from there to there. So each one I've got what proportion fell in those ranges. Okay? And I've just connected these things so I can see this. If you look at the darkest group at all, that's where 90% of the values generated from a normal 0, 1 appear in a QQ plot. So you immediately see that these blue guys are far, far away from anything you would ever see just generated from a Gaussian. So it's kind of obvious that that's not Gaussian. Okay? Any questions? Yes? Ah, good question. So how does QQ test know which distribution to use to make the bands? It doesn't. You have to tell it. The default is a normal. Okay? So this is assuming that it's a normal, which is what people often look at. That's why it's a default. But you have to tell it which distribution you're interested in. Everybody understand how these are constructed? Any questions? Yes? More? It's stupidly simple. Okay? You imagine you've got this Excel spreadsheet and you've just ordered each sample. So you know you've got the smallest ones. So that's a sample of size 1,000 from the smallest values in a sample of size n from Gaussian. Okay? So it's stunningly simple. Which means, why not do this? Because it'll give me an envelope here of saying, give me some guidance to see whether or not I should get excited about this. And I should definitely be excited that that is not a Gaussian. If everything I did depended on that data being Gaussian, I'd be in trouble. Okay? Other questions? All right. So some notes here. So one thing that's funny is that you notice that the normal 0, 1 goes from -3 to 3, centered at 0. But our data actually appeared to be, these are durations in minutes, so they appear to be values between 1 and 6, or slightly less than 1 and less than 6, which is a different location and scale. That curve, these envelopes are on as if they match the location and scale. So QQ test has to do a little bit of work from the data to figure out what's a sensible location and scale for this data, and then it does the location scale transformation to these guys. So if it figures out from the data that the scale should be 2 and the location 3, right, it multiplies everything by 2 and here and adds 3. So there has to be a little bit of work. It's trying to do some estimation underneath the covers. Yes? No, you can also choose different intervals. But the defaults are 90, 95%, 99%, and the whole range. So if I were to call this again, I'd get a different plot. That in the sense that the envelopes was changed slightly because they're all from simulations. All right? Questions? Okay. The other thing that's you need to know is that I'm building these intervals, or QQTest is building these intervals based on the smallest values here. So as if these guys, this is the central 90% for the smallest one, the central 90% for the second smallest one, etc. But we're connecting the dots here. So these are all point-wise intervals, and we're making them as if it's a whole envelope, right? So it's a little bit misleading in the sense that we don't necessarily expect, it's not telling us anything about how one point is related to the other. For example, you could not have a point down here and a point up there and a point here and a point there because they're ordered, right? So the envelope is not taking into account that the points have to be ordered going from smallest to largest as we go left to right. Oh yes, the other thing is the default values, which you can't see. Well, let's just look at some. You can actually show on the axes the probabilities, okay, rather than just the values. So here again, now this is the cumulative proportion, so you can see where the median is in the normal data and where the median is in the data itself. Median in the normal distribution and in the hypothetical distribution, which is Gaussian here, and the median in the data. So you can change these things so you can actually see the percentiles, the proportions that you're matching on. Okay. So let's look at Galton's, women. Something else that you can do is there's this function here that we actually have. Remember, it doesn't have real data, but rather it's got the centers of these bins and the proportion of women there and the sample size. So we don't have 775 points in Galton's data. What we have are the sitting heights at particular proportions. So QQ test will take what is the sitting height, what proportion does it correspond to, and how big was that sample size. Okay. So there's Galton's data. And what do you make of that? Does Galton's data look like it's Gaussian? Definitely, right? It's almost smack on a straight line. If anything, it looks suspiciously too good to be true, right? You wonder whether there was some adjustment made to make this look like it's Gaussian. So it definitely looks Gaussian. You can see the narrow bands. It lies within it, but it's suspiciously good. Oh, right. So compared to remember the ogive, if we just had the quantile plot, we wanted to see, does it look like a curve that looks like a Gaussian quantile function? Back to back, just looking at the straight line, it becomes very much immediate. Right? So ideally, I mean, what you want to have is when you've got the data actually come from the hypothesized distribution, you would like the test statistics, in this case a QQ plot with those envelopes, to indicate no evidence, or very rarely indicate evidence against that hypothesis, right? So-called type 1 error, right? False rejection. And now you'd also say, well, when it's not Gaussian, I'd like to be able to detect that with high probability. So it's worth looking at a bunch of null configurations when the hypothesis holds, and also some non-null configurations when it doesn't hold. So first we're looking at how good is this test doing when we are generating from normal 0, 1, let's say. So these are sample size 10 and 30 from normal 0, 1. So 10, remember when we were looking at these beforehand and we were just talking about is it a straight line or not? And you might have overinterpreted these things. Now it's protecting us a little bit in that all of the points, even though there's a bit of curvature there, they're all well within the bands. So don't get too excited about it. Okay, it seems to be in agreement with data that comes from a normal 0, 1. That's the y equals x line. So it's again suggesting that the location and scale in the sample is different from what was generated, but it's not anything that doesn't look normally distributed. Okay, so the bands are produced by 1,000 simulations from normal 0, 1. That data we know really came from a normal 0, 1. So the null cases, these seem to look like it's doing the right thing, right? You're not going to get excited about that. When n equals 30, again, these guys are well within the bands here. They look like nothing to get excited about. The wheels came off somewhere. So that's going to be a false positive. We're going to say that doesn't look normally distributed. And it's true. So that data set does not look normally distributed. We know because we played God here that it gets to that we generated from a normal distribution. So that's a false positive, type 1 error. And hopefully we have fewer of those with the bands than we had without the bands. Okay, any questions? Okay, so in the non-null, we're going to look at things that are, you know, when it's not null, we'd like to reject it all the time, and we worry about when we don't reject it very often. So here's a chi-squared on 3 degrees of freedom with a small sample size. And if we're looking at that, that doesn't look, sure, that looks normal. That could have been generated from a normal distribution well within the bands. Same here, just not being able to detect these differences very easily with small sample size. With small sample size, it's really hard to tell the distribution that it comes from. Well, there's some clangers. That one we'd say maybe that one doesn't look normally distributed. So that's a good thing. And maybe this one's got an outlier here, worries it, but it's on the edge. That's a very unusual point. May give us some cause for concern. It's outside the 99% interval for the largest point. In 1,000 replications, we only saw 1% of them as large or in either direction as that point. Okay? Or 0.5% on that end. 30 becomes a lot easier. As the sample size goes up, it's a lot easier to detect. Again, this one, I don't know, there's some curvature there, but should I get excited about that? It's certainly within the envelopes, but is that an unusual configuration of points? Remember, the envelopes aren't telling you how the points typically arrange. They're just doing them one point at a time, one vertical strip at a time. This is definitely doesn't look anything like a normal distribution. Again, this one looks like it's outside, nothing like a normal distribution. These points are all, we got 4 or 5 of them that are very unusual. And here, you're seeing some outliers on this side. That's a little bit worrisome, but it still looks, you know, not nearly as bad as these other points. So as the sample size is increasing, it's becoming easier to detect. Again, 50 here, certainly 3 out of 4 of them are obviously outside. This fourth one again has some guys that are far too small on the left and a lot of curvature. So you think about what's the shape of that compared to a typical shape inside there. Okay, any questions? So large numbers of points outside of the envelopes or some points very far outside indicate evidence against the hypothesis that the data came from that particular distribution. We want to look at another non-null. That was a lot of asymmetry, looking at a symmetric non-null with a t-distribution. 4 degrees of freedom, sample size 30. So this looks non-normally distributed on the 2 ends here. This one a little less so. That could be normally distributed. That definitely looks like it's not. Yes? So the question is, how can I distinguish between outliers from a much larger tail that generated it? The question is, what do you mean by outliers, right? And that's something that we can sort of recognize when we see one, but we'd rather have an actual algorithm make rule for deciding on that. In every one of these cases, if you see an outlier, these outliers here, you could either say that it's come from another distribution generated but with a heavier tail, or it's come from a normal, and we've generated here 5 really unusual points, because when I generated 1,000 of them, none of them got anywhere near that size. So you still have the same problem. Is any significance test? The hypothesis is if it came from a normal distribution, right, then I've observed something unusual, highly unusual. The more unusual it is, the more evidence I have against the hypothesis that it came from that distribution. I happen to know that it came from a T on 30 degrees of, on 3 degrees of freedom. Oh, that's n equals 30. I was saying the degrees of freedom was equal to 30. That's wrong. So that's degrees of freedom are 4 and 3 here. So these are less heavier tailed and these are more heavier tailed. So to answer your question, it's 2 ways of saying the same thing, pretty much. It could have been generated by a heavy tail distribution. Those are outlying points. So heavier tail distribution in the bottom row, slightly less heavy tail distribution in the top row, degrees of freedom 4 and 3. And for some data sets, you can't, it doesn't look like the anything too non-normal. And for others, it definitely is picking it up. Again, when we look at this, the envelopes are just saying the range of these things, but what the envelopes are not taking into consideration is that curvature that we see, this sort of pattern, is that an unusual pattern? Right? So 2 degrees of freedom and 1 degree of freedom, so we have a Cauchy at the bottom. Cauchy generate, again, some massive outliers. So these are shouting at you that there's something wrong here. For 2 degrees of freedom becomes easier to detect than 3, and for 1 much easier altogether. But you could still get a configuration that you're not quite sure about. This looks like it's got 2 points here together that are farther away than 99% of the points generated from a normal. Okay? So it's still not perfect. It's adding an awful lot of information to the plot than just looking at the QQ plot by itself. But it still requires, there's still some cases where you're not quite sure, and you have to realize that having a couple at the edge is much more significant than having just one at the edge. Okay? So, n equals 50, 4 degrees of freedom. We were hitting outliers, a couple outliers here. 3 degrees of freedom, more frequently outlier. 3 degrees of freedom are getting easier to tell. So 2 things are happening. As the tails get heavier, it gets easier to tell the difference. As the sample size increases, it gets easier to tell the difference. And down to 2 degrees here, again, that one looks pretty darn good, doesn't it? Even though it's generated from a T on 2 degrees of freedom, it looks well within the envelope of a Gaussian. Another sample, way out, right? And as this sample size increases, you're expecting to see a greater probability of generating these things that are way out, so it should be easier to detect. When it's down to a Cauchy with 1 degree of freedom, there's lots outside. These tails are just so heavy. Okay? Questions? So, as I said before, what we've been looking at are those envelopes, and they're just telling you, are these points one at a time, are they within the range? But it's not telling you about that connected curve. Is that an unusual shape of curve? To get a sense of the unusual shape of curve, I'm going to have to look at a number of different possibilities, right? So let's look at some here. So I've got T data, sample size 30, 3 degrees of freedom, and I'm going to turn, so with Q2 test, I'm going to turn the envelope off, so it's false, and this is what a regular, that would be your QQ norm. That's what standard QQ plot would look like, and this one has got such a large outlier that you may say that maybe that's evidence against the hypothesis that it's normal. So the question is, it looks pretty good most of the way except for this funny value down here. Does that configuration actually look like any configuration that would come from a normal? So what we're going to do is use so-called exemplars, just some examples with different colors, and it's easier to show you than to talk about. So that the colors are now curves. Those are little QQ, those are little QQ plots for 5 different samples. And so you can see that these curves all seem to go together in this particular way when they come from a normal, and this black curve has got a rather different behavior. It's come down here and it's got this tail going off down here. So these, by having a bunch of examples, you can actually see what does the shape of these curves look like. So it's trying to get some joint information across all of the points at once. Make sense? Okay, so if you do lots and lots of these exemplars, right, so 50 of them, so this is the number of exemplars. instead of just 5, you get a lot better sense of what the pattern is overall, but you start to lose each one of these individual curves. In fact, these are how the envelopes are constructed. Right? I produce 1,000 of these and then mark off where the 90% point is, the 95% point is, etc. on each one of these. But now to see the curve, you'd actually have to follow one of these colors, and that becomes impossible. Right? So there's a trade-off here in that with the exemplars, you can only have a few of them to get some sense. But if you only have a few of them, maybe you haven't seen enough to see all the variety. So it's kind of this trade-off. So sometimes you use the envelope, sometimes you use exemplars, and you could in fact use both. So to keep ourselves honest, we could do a lineup test, and that's possible in the QQ test. So you say do a lineup and no envelope, so this is going to look like regular QQ test. And now you say, okay, the data is one of those. Which one is it? Right? Which would you pick? So I would pick 20, but we've been contaminated because we've already seen the data, so it's a bit of a cheat. But I would pick 20 here as the curvature. I may or may not be right. That first one is mysterious still. 12. So I got completely faked out by there. And one of the reasons I got completely faked out is I was assuming that it was the previous data that I saw, which I knew went bent down this way, and we in fact had generated a different data set. Yes? No? So the question is, if you can't tell, is it likely to come from that distribution? No is the answer to that. What is the answer? No? Yes? That's right. So the answer is there's no evidence against the hypothesis that they come from this distribution. You're always looking to falsify, right? So here's another data set. Anybody want to venture any guesses of what they would pick there? Anybody have a strong view? Yes? 8? Okay, let's see whether that's true. 17. Is that the same one? 68? Yep. So in fact, it's the data were this one, 17. So again, no evidence against the hypothesis that they came from that distribution. Now we are just using the QQ plot by itself. So one last one. Anybody have a guess here? 13. And hopefully it's here. 13 it is. So that one we were able to pick out, or at least one person was able to pick out. So that's evidence against the hypothesis that this particular data set comes from the normal distribution. Okay? So that's one test statistic. That's the QQ plot that you're used to looking at, and you say, well, how would you do if we added envelopes? This is a different test. Anybody have a choice here? 3? $11. Right? So this one people might have also chosen with some curvature there in these outliers. 3 you chose because of the curvature the other direction, some outliers. We have no evidence against the hypothesis. Whoops. Here? $11. Okay, so people are choosing 11 here. And I have 20. It's this one. No evidence against the hypothesis. So the lineup test is actually keeping us honest. That you were more excited about a one that was actually coming from that distribution, which by bad luck was outside of the envelope, than you were for that one. Right. I keep pushing the wrong keys here. Another one. Five. Huzzah. Evidence against the hypothesis. So it's nice having a lineup test built into the QQ testing so that you can say, rather than choose one of these things, just say, give me this and let me pick from it. And finally, maybe the exemplars are adding a little more information. So there are no envelopes here, just exemplars. How many? 5. So anyone want to pick one here? The black is the supposed data. The color ones are examples. 6. Three. Okay, so again, no evidence against that hypothesis. Here. 1. So when you're doing this, make sure that you're looking at all of them, not the first one that jumps off, right? Because I go along to 2 and I see also an odd one. 1. Let's try 1. That was easy. You could do that one in your head. 1 it is. So evidence against the hypothesis. In the 1, I mean, you've got it going on both ends here, as opposed to this is just as one end that's out of unlike the others. Here, 11. Oops. And hopefully that's correct. Yep. So we got 2 more. We got 2 out of them with the exemplars. Just wanted to briefly go over how we ended last day, because that was a bit of a rush on these quantile-quantile plots, particularly the so-called self-calibrating quantile-quantile plots from this package called QQ test. And again, to show you that QQ test can take any of the standard distributions that are available, and also any distribution you give it. If you have your own distribution function, you can hand it the quantile function for that and calculate the self-calibrating quantile-quantile plot. So for example, we looked at last day, we're generating data from a normal, 30 observations from a normal, and we're wondering whether that comes from a chi-squared on 3 degrees of freedom. And there are lots more examples in the package. And what's going to happen is we're going to have the sample quantiles as before from our data set, just the ordered values. But these bands now are generated by generating 30 observations from a chi-squared on 3 degrees of freedom, and doing that 1,000 times to get the envelopes. So that's why you're seeing this rather different kind of a set of values, and why you can see sometimes chi-squareds will look sort of their own, because they'll be producing values that are quite quite close to the middle as well as far out in the tail. In this particular one, the envelopes are indicating that something's gone amiss on the left tail. That left tail is heavier, longer than is expected on the chi-squared 3 degrees of freedom. That's because you know the chi-squared is skewed with a long right tail, so it's got a short left tail, and the normal has a longer left tail, and so you're seeing these being farther away from the middle of the data, a heavier left tail than the chi-squared. Okay, so it's not that the normal has a heavy left tail, but it's heavier than the distribution that I'm comparing it against, the chi-squared on 3. Okay, any questions? Does everybody see that? So as before, we're going to be looking for numbers of values outside of the envelopes and also patterns of the connected sequence of dots. How does that compare to exemplars? More interesting, I want to make sure you understand this, is the notion of not having any particular hypothetical distribution in mind, except that these two sets of data are generated by the same distribution. And we did that before where we mixed them up randomly. We're going to do something slightly different now. I'm going to say, let's assume that beaver 1, the body temperatures of beaver 1 are whatever values that they are. Is it plausible that they came from the distribution that generated beaver 2, whatever that distribution is? Or the other way around. The values for beaver 2, do they look like they plausibly came from the same distribution that generated the values of beaver 1, whatever that is? And how we're going to do that is just at the board here, you imagine that you've got a quantile plot. So this is, say, beaver 2's temperatures. And I have to generate a sample of whatever size from the same distribution as this quantile. So my best guess at the actual true quantile function for whatever distribution generated this is the one I'm staring at, this one itself. So I can pretend that that's the real distribution. And now we need to generate values, that is these x values over here, from this quantile function. One way to do that is to just generate uniform 0, 1, because these are all going to be equally spaced by the p-points thing. So according to how many observations we have, here we've got, 9 observations. So you know that 50% of them are less than or equal to this point, 75% less there, et cetera. All we need to do is generate uniform. If I generate a uniform 0, 1 here, and let's say I get that value, I just go up, and that gives me the value of the x from the distribution. Okay? And I do that as many times as I need for the sample size that I need. I get generate values, and then I'll get values that come from this distribution. Okay? So that's one way of doing that. And that's what QQ test does when it's given 2 sets of data. Any questions on that? Because that makes sense? Okay. So when I look at this data, I can do the data is beaver 1, and the data that I'm testing against is that of beaver 2, right? The body temperature of the second beaver. Or the other way around, I could say the data is beaver 2, and I'm going to use beaver 1 as the distribution that might have generated the temperatures for beaver 2. And just going to plot both of these at once. So on the left here, I've got beaver 2's body temperature on the horizontal axis. The vertical axis are the values corresponding to beaver 1's temperatures. And these gray bands are generated by using exactly the trick that we just looked at on the blackboard of generating from the sample quantile function the empirical quantile function of Beaver 2. So if it's come from Beaver 2, when we generate 1,000 of these samples from Beaver 2, we get envelopes that look like this gray region here. And it's pretty clear that Beaver 1's temperatures are far outside of that region. It does not look like the body temperatures for Beaver 1 are generated by the distribution given by the body temperatures of Beaver 2. Okay? So that's pretty strong evidence against that hypothesis. And to show you the other way around, and that the envelopes are going to be different, because now I'm using Beaver 1's empirical quantile function to generate the data on the horizontal axis. That's the comparative of the hypothetical distribution that I'm comparing the temperatures of Beaver 2 to. And you see again that I've got values that are outside of the envelopes. Now if those, I added a sort of y equals x line there. So if the temperatures were in fact identical, distribution, same location, same scale, and same shape, they would be near that red line. They're not. Okay? Any questions? Yes? Yeah. Sure. So, this is one of the data sets. This is the data set that's going to appear on the horizontal axis, right here, okay? So it's its quantile function. Remember, that's a quantile-quantile plot. So this is a quantile function. And you know that for any value here, I can read off the proportion of values that are less than or equal to that, right? I can read off the value for which the proportion is less than or is that. So now I just generate a uniform distribution, a value from a uniform 0, 1. It's going to land somewhere along here. I pick that, I see where does it land, and I read off that value. I do that little n times. Okay? All right, so you can do this with samples, comparing one sample to the other, and it's a little different from saying they're both from some distribution, that is the merge of the two of them, which is what our random mixing was doing before. Now it's saying, suppose you've got one of them is actually the hypothetical distribution. What would data look like that came from that distribution? This shows that you can take any function you like. You can give it, as long as you give it the quantile function, it can do the same trick, whatever that quantile function is, and generate values. So here's a quantile function of a beta with alpha 2 and beta 2, the two parameters. So anything you're interested in could be compared. So does this data that were generated from uniform 0, 1, do they look like they come from the various betas? So arguably there's some evidence against this being a beta 2, 2, and you might even want to look at, is that pattern compared to, how does that pattern compare to the exemplars? It certainly doesn't look like a beta 1, 3, right? That's way outside of the bounds. This one also outside of the bounds on either end. Doesn't look like a 0.9, 0.9, but it looks more like a 0.9, 0.9 than it does any of the others, particularly in the middle. And if you go back to those signatures, you remember that it's very high on either end and sort of low, kind of uniform in the middle. Okay? So this is just with exemplars. So you can only use a few exemplars because they overstrike. Here, how many did we use? 10. So again, this still looks like a kind of an odd shape compared to the other exemplars. Definitely odd. Not so odd looking, maybe. Okay. Any questions? So that's where we gave a rush through that on last day. Everybody get these quantile-quantile plots? Yes? There is. It's called QQ norm. That's for quantile function, did you ask? I'm sorry, I missed the question. Yeah, so there's a function that's called quantile that you can just get the values. And if you do quantile at a data set, it'll get the quantiles. I believe that's correct. Okay. Other questions about these? So the advantage of that is that self-calibration. It's giving you a little bit more information on how excited you should get about what you see compared to a simple QQ plot by itself. All right.